The last thing that we'll talk about in our queuing theory topic is what I've humorously or otherwise titled Queuing for Performance. And what we're going to do is look at a performance model that we have some data about a system. It's serving web pages, and we know stuff about how many web pages are going to be used and how many disk accesses there are, and how much the CPU usage is and what have you. And we can use this to make some statements about what is the bottleneck device, and what is the maximum transaction rate and the average transaction time. So this kind of thing is useful in a scenario where somebody says, look, given the hardware that we have, how much load can we support? Like right now, if there are 1 million users using the product, and we don't upgrade things, we don't buy new servers or anything, what is the maximum number of users we could support with what we've got right now? Sounds good. It's useful in scenarios like, should the ECE department get another, ECE Tesla server to support people who are doing a GPU computation? You can do this kind of math, you can figure it out, and you can work out in the end whether the GPU is in fact a bottleneck device, and what is the maximum transaction rate. How many more students can take ECE 459 before someone in a server room starts crying? I guess we'll find out, won't we? All right. We have 8 steps to getting there. The first one is convert everything to common time units. That feels like it should almost go without saying, but I said it anyway. That if you are working on a you're working on a data set of some sort, you need to be working in common time units, otherwise your numbers don't make sense and you get the wrong answer. So, okay, let's not forget to do that. We will calculate the visitation ratios. This is how often various components of the system are used. We will figure out the device utilization. So what is what devices are being used and how much? How close are they to capacity? We can calculate the CPU service time and the device time. So how much time the CPU is spending doing stuff and how much time devices are spending doing stuff. And we will then be able to identify the bottleneck device. And given that allows us to answer the what if type questions where we say, all right, what is the maximum transaction rate and what is the average transaction time? So we'll start with this as our known data. We have a web server. It serves 9,000 pages per hour, and our known values are this. Every hour, there are 9,000 web pages served. The average utilization of the CPU is 42%. There are 108,000 hard drive accesses, each of which takes, on average, 11 milliseconds. There are 72,000 accesses to a second hard drive, which on average takes 16 milliseconds. And there are 18,000 network accesses, each of which takes about 23 milliseconds on average. The 2 network accesses for every web page make sense. There's receiving the incoming request, and then there's sending the response. So you would expect that those figures would line up. And for processing every request, there's some number of times we have to access disk 1, and some number of times we have to access disk 2. Again, we're looking at just counting those things, which means we can compute an average as we need. All right, we'll convert everything to a common time unit, and for this I've chosen seconds. Great, done, easy. Add a couple zeros at the front here. We're using the right time units, and no more milliseconds. Great. The other thing that we can put down here is lambda, and this is the reported counts divided by seconds in the reporting period. So if there are 9,000 pages per hour, then that's 2.5 per second. Okay, good. Let's do it. And that means 30 disk accesses for disk 1 and 20 for disk 2 and 5 for network. All right. Doing well so far. Everything is thus far making sense. The visitation ratio is the number of times a device is used in each transaction. So divide use by the number of transactions. You could also log the visitation ratio if you wanted. There's no reason why you have to do this, but if you're calculating it, then let's do that. So web pages, for each one visit, there are 2 network accesses, there are 12 disk 1 accesses, there are 8 disk 2 accesses, because we're just dividing these values, and the CPU here, visitation, is the sum of all the other visitation ratios. Why? Suppose we do a disk read. The disk is visited, and when the disk read completes, we go back to the CPU, and then it picks up the data that's just been shuttled in from the very slow hard drive, and so the CPU has to be involved with every operation, and for that reason, it appears in there as the sum of the other values, hence why it's 23 in that scenario. Okay, so having divided the use by number of transactions to get the visitation ratio, we can calculate the utilization. I mean, we know that for the CPU, and we can fill it in for disk. It's, again, just rho equals lambda times S. Same for disk 2, same for network, and there we are. In this table, we show percentage for the CPU instead of a decimal number, so obviously you can just replace that. And you can also fill in the service time and lambda for the CPU. Lambda for the CPU is just the sum of the other ones, as we've discussed, as same for visitation. And by just swapping around the formula for rho equals lambda times S, you can solve for S for the CPU and complete it. And so that is easy enough, and there we have it. And then device time is the final thing. The header in the column for device time is actually just V times S, so visits times service time, which is saying, all right, every time we are visiting the disk, it takes a certain amount of time. If it takes 0.011 seconds and we visit it 12 times, we'll just multiply that to figure out how much time we spent visiting that disk in total. And there we go. That allows us to complete the whole thing. Did we need to complete the whole thing? Probably not. In a practical sense, the most valuable column in terms of figuring out what is the bottleneck is the row column utilization. The bottleneck device, i.e. the one that limits our maximum throughput, is the one that is the busiest. In this case, the application appears to be CPU bound because we're using about 42% of the CPU, and that's well ahead of disks 1 and 2, each of which is used at about 1/3 capacity. So, given that, we know now that the CPU is the bottleneck device. We can use that to make a prediction. And our prediction will tell us what the maximum rate of transactions web page requests is, and it is going to be calculated as 1 over SIVI, I being the row in the table that is the limiting factor, and we know that's the CPU, so it's the second row there. And that means 5.95. That's the maximum rate of transactions that we could observe. So like our incoming rate is 2.5, and if lambda gets to 5.95 or more, we can't keep up with the incoming requests. And using the table, you can also calculate the average transaction time, and it's the sum of the visitation columns, so you just add up the V times S for each of them, because when we are doing this, all right, we visited the disk 12 times, so that for a total of 0.132, and we visited the CPU 57.5 times for a total of 0.168. And so on, and so on, and so on, until you've added up all of those things, so you get the average transaction time, which tells you when a call arrives at the web page, how long does it take before it is completely done, all the way from receive the incoming network request, all the way to send the outgoing response. So, yeah, at this point, we've calculated kind of everything that we need. And we've got a pretty good idea of what our limitation is and what will the system be able to tolerate. So if you know this about your system and your boss says to you, well, we expect that there's going to be a big increase in traffic in the next month, and we expect that web pages will go up to an arrival rate of, 4, like lambda equals 4, you could say, yeah, that's still within our capability of handling, so I think we're good. We don't have to make any changes. All the utilization rates will go up, but we won't be limited. We won't be failing to keep up with those requests. So that sounds pretty good. I'm sure your boss will be happy to hear that you don't have to buy more hardware or rent bigger instances and pay more money to handle the expected increase in traffic. That sounds like exactly the kind of thing a manager would want to hear. Now, ultimately, of course, this is sort of predicated on the assumption that when we say like utilization of the CPU is the limiting factor, that things remain. Again, I'll put in quotation marks, kind of nice, that things like don't get out of control somehow, whereas the disk gets closer to saturation, its performance gets worse. That kind of thing could happen, but we're assuming for the sake of this what-if calculation that it doesn't. If you find that with lambda equals 4, you're now limited actually more by disk 1, you would just rerun the calculation. When you get there, and you would say to your boss, look, we were able to handle the change to 4, but if we want to go up more than that, it's going to be a problem, and that would be okay. That kind of thing is one of those real-world difficulties that we like to pretend don't exist when we are working on a hypothetical problem like this, but we do have to kind of acknowledge that it could be the case. Okay. The typical assumption, though, is that we know the service times for each device, but sometimes that's not true. Sometimes your performance monitoring, the things the operating system gives you, just tell you the average size of a device queue. So you have to work backwards from there to get the service time, and that's not super hard. The average size of the queue is rho squared divided by 1 minus rho, as we saw earlier, if it's an MM1 queue. And if we put this together with the average arrival rate lambda, so we're just substituting in the value for rho to work out S, then we actually end up with W equals lambda S squared divided by 1 minus lambda S. If you rearrange and solve for S, you find negative W plus minus W squared plus 4W divided by 2 lambda. Oh no, the quadratic formula. Were you one of those people who thought when you saw the quadratic formula in math class, what am I ever going to need this for? When will I ever use this? Quadratic formula strikes back.